Welcome back to our fault tolerance discussion. So let me take you back to our outline slide from last time. So we have these 3 or 4 rather points on our menu in the fault tolerance part, and about the first 2 we have already spoken. So most importantly, we explained last time how quantum error correction works with 3D cluster states. Now you don't want to only do quantum memory, you want to do fault-tolerant quantum computation. And today we talk about how we do fault-tolerant gates in this setting. So that's coming up today. And then there's also performance characteristics to discuss, namely what is the threshold of this computational scheme and how does the operational overhead scale. So that's all that we'll talk about today. So now let's talk about encoded fault-tolerant gates. This is a preview of what we are going to talk in this part of the lecture, how the braiding of defect strands relates to gate action or implies gate action. Yeah, in order to explain this to you, I want to use a trick. Namely, I want to map the 3D cluster states to 2D surface codes propagating in time. So a fact that already came up in the first lecture, then applied to 2 dimensions, is the following. When we are translating measurement-based quantum computation to the circuit model, then the dimension of the setting is reduced by 1. And that's because one direction in our picture here, the horizontal direction, on the cluster becomes the circuit model time. So one less spatial dimension remains. And that's true in all dimensions. So if we apply this to dimension 3, to the 3-dimensional cluster, then what we see is that we have a surface. Our quantum register is a surface, and we have this 2D quantum register propagating in time. But there is one more thing to say here for the 3D cluster states. Not only do we have a 2-dimensional quantum register, also is this quantum register encoded with the surface code. So the 2D quantum register is actually a surface code of a bunch of logical qubits. Okay, so you see, for the way we are explaining it here, we need to talk about the surface code. And how do surface codes encode qubits? They encode them in the simplest fashion in their topology. So we know that a torus can hold 2 logical qubits, and we are dealing with a topological code. So this property is independent of the size. It's related, in fact, to the genus of the surface. So if we have something like a torus but with more handles in it, then we encode more logical qubits. In fact, the capacity of the surface code, of the toric code, equals twice the number of handles in the surface. So that's the main idea for how to get logical qubits into a code surface. So for example, if we have just a segment of the plane with unsuitable boundary conditions, then we get no qubit at all. And if we have suitable boundary conditions like smooth and rough, or the other way around, then we have 1 qubit encoded. And that is the important fact for us. So we don't need to go to complicated topologies. We can do it all in the plane when we introduce boundary in suitable ways. And all we have to do for our setting is to go from the plane with exterior boundary conditions to the plane with holes. So we will create internal boundary in our setup. This is how we will encode the logical qubits. Okay, so the main thing was already said, but let me just get a little bit back into the surface code and into the discussion of what holes are and so on and so forth. So what you see here in this one panel is the stabilizer operators, plaquette stabilizers and site stabilizers, and the encoded Pauli operators X and Z. So just as background information, maybe to retrieve from way down in your memory. So this is what the surface code looks like. And what we use here is the surface code with holes. And what is a hole? A hole is a missing stabilizer. So we have primal holes, these are missing site stabilizers, and we have dual holes, which are missing plaquette stabilizers. So missing means that these stabilizers are not enforced. And if we do not enforce certain stabilizers, this means that the code space gets larger, and this is how we get encoded qubits into our setting. All right, so this is what the holes mean in the code surface, and how are the holes related to our computational scheme. So remember, we had these defects in the three-dimensional cluster states, which were just cluster material, so to speak, missing. And now, if you make a time-like slice through your cluster state, then a defect becomes a hole. And these are precisely the holes that we are talking about here in this picture. Now, we need to talk about how holes relate to encoded qubits. So in our case, every logical qubit, every encoded qubit is made up by two holes. And this is what's shown here. So there is a primal version and a dual version. Remember, missing site stabilizer and missing plaquette stabilizer. And yeah, so what we now need to talk about is how, in this scenario, what the encoded Pauli operators look like. So for the primal qubit, the encoded X wraps around the primal hole, or one of the two primal holes, and the encoded Z moves between these holes. For the dual qubit, it's the other way around. So here the Z wraps around the hole and the X moves between the holes. Okay, so in our setting, these are the encoded Pauli operators. Please remember that we will use this information in a critical way. It's going to be very important for our scheme. Okay, so now we are ready to explain gate action. So here's a situation where nothing happens. So we have a surface code surface with the holes just sitting there doing nothing. They just stay in place, and so their timelines, which are the defects in the 3D cluster, they just kind of stretch out like parallel lines. So nothing happening here, we have just memory. All right, but now something does change. Suddenly, two of these defects are being braided. So it's a monodromy, in fact, so that every hole ends up in precisely the same place where it started. All right, so this, I claim, is a CNOT gate on our two encoded qubits, and I want to show to you why this is so. And this is what you can see here. So also for reference on this screen, you see the two types of encoded qubits, the primal and the dual. And you see here in our construction, we have precisely that. We have a primal encoded qubit and a dual encoded qubit. And so what we are now doing is we are looking at the dual encoded qubit in black and the encoded Pauli operator X. It's represented by an X string stretching between the two holes. So that's what we have. So look at the orange panel there. This is our surface code surface, and you see the encoded Pauli operator sigma X sitting there. Okay. And now we are propagating it forward in time in such a way that its endpoints remain attached to the respective holes. So that's what we require for an encoded qubit. Okay, so X string moves forward, we go to the second instance. As the hole moves to a different place, the string has to follow, it stretches a little bit, and then something more drastic happens. The blue defect representing the primal hole is getting in the way. So it's really moving into places where the Pauli X string likes to be. But yeah, so the Pauli X string cannot end in the primal hole, so it must move away. And you see it bulging out more and more and more as we go along. So at some point, when the primal hole near the end of the evolution is back in its original place, then you find that the X string has now basically a loop added to it. And we can split off this loop and go to the last instance of time. And what we then find is we have the string that we started with on the dual qubit, but we have also a loop on the primal qubit. And now we go back to our dictionary and we look what that is. So the extra X-type loop, it turns out, is an encoded X on the primal qubit. So the way to read this is that under the action of the gate, the Pauli X string on the dual qubit has been propagated into the tensor product of an encoded X on the primal qubit times an encoded X on the dual qubit. Yeah, and so that's a propagation relation that you know from the CNOT gate. That alone doesn't identify the gate as a CNOT gate. There is a couple more relations that we need to look at, which, however, in the interest of time, we don't do here. So that would be a homework assignment. So what we've done is, in a topological way, explain how the sigma X on the dual qubit propagates. You would also need to do this for the sigma Z, and then for both Pauli operators on the primal qubit. And if you do this, what you get are the propagation relations shown on this slide. And from those four propagation relations together, you identify the gate as the CNOT. Good. So this was the explanation for the CNOT. I hope you understand it, or you understood it. So that was basically the main message of this whole lecture, to explain to you the topological gate. So here on this next slide, you see the entire list of topological gates that one can do. And you see there is a CNOT here on the slide, and you also see that's not exactly the CNOT that we explained. And the reason for that is the gate that we did explain was on a primal and a dual qubit. We want CNOT gates between qubits of the same type, and that's the CNOT you see here. It's a tiny bit more complicated, but the explanation is essentially the same. So if you are so inclined, you can fill the gap by yourself. The other topological operations you can do are preparations and measurements in the X and Z basis. Yeah, so the topological gates that I've just shown you, they are not universal by themselves. They are all stabilizer operations. And so something else is needed for universality. And now finally, if you wondered, this is where the singular qubits come in place, or why they come into the game. So what you see here on this slide is a singular qubit held in place by two strands of defect. And when all these qubits are measured in their respective bases, what the effect is the preparation of a T-state. Remember, the T-state is the magic state in quantum computation with magic states. So this is a preparation of that state, but not a fault-tolerant preparation. And so what you now need to run is magic state distillation using the topological gates already explained in order to get a T-state of high purity. And once you have that, then you can do state injection to get the T-gate. And with that, in addition to what we've already shown, you have computational universality. So that completes the universal fault-tolerant gate discussion. Okay, Now that we have seen the computational model, how it operates, let's look at its specs. Let's look at its performance characteristics. So the most important of these characteristics is the fault tolerance threshold. Yeah, so remember the threshold theorem, it just said that there's a non-zero threshold below which you can compute arbitrarily long and arbitrarily often. But now let's assume this error threshold is 10 to the minus 50. Then it's a nice theoretical result, but without practical ramifications. On the other hand, if the error threshold is high, like 1% or 10%, then you can achieve this with current or near future technology, and then it is of technological relevance. So the value of the threshold matters, and we want to know what it is in our case. The second thing to say here is that an error threshold always refers to an error model. So what error model are we using here? So we use an error model with probabilistic Pauli errors. So dices are rolled, and depending on the outcome, well, certain Pauli errors happen or not happen. Well, that is not the most realistic decoherence model by far that you could think of, but it is actually not too bad. And it's the error model typically used in analyses like these. Okay, so we need to model various operations. We have operations in the preparation of the cluster state, so individual qubit preparations, entangling gates, and other gates. And then we have measurement that we need to model. Also, the measurement will be erroneous. And sometimes we may or may not have just qubits sitting idle, and then there's going to be memory error. And all these errors need to be taken into account. So we say we have probabilistic Pauli error. So these erroneous operations will be associated, each one, with an error probability. And for simplicity, just to be able to get one number out, we set the error rates for all these processes equal, just as a simplification. There is one more assumption that we need to make, and that is, we don't even need to, but we make it anyway, and that is the assumption of fast classical processing. So there's never going to be a delay because of the correction due to the syndrome not having figured out yet. Good. So next to the assumptions that I have already mentioned, there's a few background assumptions. So locality. So the Pauli errors that we consider, they happen exactly where the gate acts that they correspond to, exactly in the same location. So for 1 qubit gates, it's the same qubit. For 2 qubit gates, it's the same 2 qubits. Independence, so the errors corresponding to different gates in the creation of the cluster state or in the measurement, these errors are independent. Okay, and we're dealing with a probabilistic error model, as I already discussed. So all these assumptions can be relaxed. They are not absolutely necessary, but in our numerical simulations, this is what we assume. Okay, and under these assumptions, we come up with the following thresholds. So there's two. So there is one for the topological error correction in the V region that I explained to you, and that's 0.75%. And then remember the last gates I showed, magic state, preparation, and injection. That operation has its separate threshold, and it is higher. And so, yeah, it's above 2%. And so the overall threshold is set by the smaller of the two, and that's the topological threshold. Again, overall threshold value 0.75%, potentially in range or almost in range of technology. So such error rates, or even in fact quite a bit lower than that, have been realized in small quantum computers to date. And so now the question is, can you keep up these low error rates as the quantum computers are grown? So the second aspect to talk about is the overhead. So let's begin with the scaling. So that's the first thing to look at. How costly is fault tolerance? And what we find is that the operational cost with error correction only incurs a polylogarithmic factor, polylogarithmic correction. So suppose you have your original computation without any need of quantum error correction. So let's assume the size of that circuit is S. And then the operational cost with error correction is that same as times logarithm of that size raised to the third power. So polylogarithmic correction for error correction in the computational cost, scaling-wise, this is very, very mild. However, if you look at the absolute cost, then it's actually really rather horrendous. So what you see here in this plot is the cost of an individual gate. So that can be an individual encoded CNOT gate or individual T-state injections or S-state injections. And you see in absolute numbers, the operational overheads for these gates are extremely large, and they are getting larger the larger the computation as a whole becomes. The good news, and that was the news from the previous slide, when you make the computation larger, the cost doesn't go up much. But even at small sizes, the cost is already very large. Yeah, so there's two more things to say here. First thing to say, the numbers you see here are at 1/3 of the error threshold. So this is still pretty high error rate. And the first thing that this plot probably tells you is that you should go to lower error rates, maybe 1/10 of the threshold or even lower. So just passing the error threshold isn't quite good enough. The other thing that this slide tells you is that there's probably lots of room for improvement. So that is work for you, probably beyond the level of homework assignment. Let me summarize. So I have explained to you how to do fault-tolerant quantum computation in the measurement-based model. And there were two important ideas involved. Namely, the cluster state is a fault-tolerant substrate. I mean, it has fault tolerance built in, you just need to use it through measurement. And the second idea was that if we put structure into the cluster state by drilling holes into it, then we can do topologically protected encoded gates in this fashion. Error threshold pretty high was the third comment to make here. And I have one more thing to say. So as you recall, we already used the mapping from 3D cluster states to a 2D surface code propagating in time. We use this as a tool to explain things, but you can make this mapping physically, and instead talking about 3D cluster states, you talk about a surface code propagating in time, and that is just as reasonable a physical system. So you have an analog construction in 2 dimensions, so something that you can print on a silicon wafer. Yeah, same threshold, same operational overhead scaling in 2 dimensions. All right, so this is all to be said about fault tolerance in measurement-based quantum computation with 3D cluster states. Next time, we will talk about quantum computation with probabilistic gates, and that's related to MBQC with photons.